Hello, calculus fans. So we studied springs in an earlier section. This time, let's imagine a mass attached to a spring that's hanging from the ceiling. Now we studied Hooke's law, and that says that the force exerted by a spring is proportional to the distance that the spring is stretched from its equilibrium. We also used the phrase natural length. So we said that f of x is equal to k times x. Now we'd like to be more precise about it now, and what we'll really say is that f of x is equal to negative kx. The reason is that the force that's exerted by the spring is a restoring force. It's pushing in the opposite direction that the spring has been stretched. Now we'd like to make some simplifying assumptions, like ignoring air resistance and friction. And in that case, Newton's second law of motion will give us a differential equation. Because Newton's second law of motion tells us that force is equal to mass times acceleration. Acceleration is the second derivative of the position function. So that tells us that m times the second derivative of x with respect to t is equal to negative kx. The left side of this equation is force, or to put it another way, using Newton's second law of motion, force is equal to mass times acceleration. Now this is going to give us an example of a second-order differential equation, and that's because it involves a second derivative. Okay, that's all for now.